Hi everyone, good evening. First of all, I would like to thank the organizer for letting me inviting me to present our work here. So I say our work because this work has been done in collaboration with Juan José García Ripoll, Gabriel Jaume, and Maria Ita. The first two are in the CSIC, in the group of QInfo in Madrid, and the third one has recently moved to Kilimanjaro Quantum Tech. This Kilimanjaro Quantum Tech is trying to build from scratch, more or less, a quantum annealer, and many of the things that I'm going to say now, you have to put it in this context. We want to do theory to develop. Someone has told us, how can we do a quantum annealer? Well, we started to review everything and see what can we improve from scratch. In the title is hardware requirements for useful superconducting quantum computers. So for here, the only thing that I need to explain, useful means that you can do something that classical computer cannot do. Okay. And then let's move. So specifically, this talk is about quantum materials for quantum technologies. And with quantum materials, what I mean is superconducting circuits. And the basic ingredient is going to be a Josephson junction. You are going to have also capacitors. You are going to have inductors. And what we want to do is to do a bridge to connect these superconducting circuits and be able to do quantum computing. And with quantum computing, I want to stress that there are two models. Probably the gate model is the one that is more familiar to everyone. In the gate model, you have a set of qubits. You have 1 qubit rotation, 2 qubit rotation, and you do a recipe that is your program. And at the end of the day, or at the day of the algorithm, you get the answer of your problem codified in the state of your qubits. But you can also have adiabatic quantum computing. This paradigm is an analogic one that you don't have gates. You deform your Hamiltonian from an initial one where the ground state is easy to prepare to a final one where the ground state of your final Hamiltonian has encoded the solution of the problem that you want to solve. The way that you extrapolate between one and the other, those are details, but basically you can use something like this, is to put a lot of weight in the H0, which is this one, and to transfer this weight in the Hamiltonian to the final Hamiltonian, that has the problem codified in its ground state. So, from building blocks, we want to design qubits and connection, no? This is the task of a theoretical guy who would do in this field. And the first thing I want to stress, what are the bottlenecks in doing this. For doing this, let me go to the basic bricks that you use to build these superconducting circuits, and the basic brick, the basic ingredient is a superconducting qubit. So this is basically this, a Josephson junction that couples two superconductors with a phase difference, which is this one. Then you may have a capacitor, well, you have a capacitor and an inductance. And then you have the different families of qubits that it depends on the parameter space of the point in the parameter space that you are. No? You may have a charged qubit where the relevant energy is the charging energy. The charging energy in the charged qubit dominates everything. So your qubit is a charged qubit. The wave function is pretty much concentrated in a couple of charges state. But you can have also a transmon that is supposed, that is better, because what you do is you increase EJ, the ratio EJ over EC, and then you make that the charged qubit is not so prone to have sensibility to the charges, to the offset charges. You can have also fluxonium and flash qubit for these ratios, and this is, I'm going to discuss about them a bit more slower because they are to be important for what I'm going to talk in the next slides. And then, yes, for the flash qubit, you again have a loop like this, where this U means the inductive energy. I put a box because you can use a large inductor, or you can use a couple of Josephson junctions. And for instance, in this flash qubit from the group of William Oliver, you have here the Josephson junction, this one, and then you have here also these two other Josephson junctions that are playing the role of an inductor. For the fluxonium, what you do is to replace these Josephson junctions, this inductive part, by an array of Josephson junctions, so to have a very large inductance. And EL is small. Okay? Well, there are a couple of nice features of these qubits, and all of them can be understood using the picture particle moving in a potential. This potential is created by the inductive and the energy, Josephson energy part of the energy. Then, for the flash qubit, what you do is you thread the magnetic field, the flux at half frustration, and then you have this potential. This potential has two states at the bottom of each well, left and right, and what happens is that they hybridize pretty much in the same way as the hydrogen molecule, and you have the splitting here of the qubit state, which is pretty small, or it could be pretty small compared with the difference from the qubit subspace to the cited state. And this is a very nice feature for some tasks that we will discuss after. You can also have the fluxonium at zero magnetic flux threading the loop, and you have this potential shape, and then you have a different physics. We described this with a spin 1 state. Even if you are interested in the qubit physics, you need to describe the three low energy states. Okay. The important point of what I'm going to talk in the next slide is that. Yes. Maybe it's going. Thank you. Okay, the important point for all of this is the first thing is to see the decay, the times, the coherence times, and with the coherence times you can roughly say this is a conservative number. These are conservative numbers. That transmons has something like 0.5 milliseconds. Probably they are now in the range of milliseconds. Fluxonium, you can say that there is 0.1, although there is a paper by a group in China that they reported 1 millisecond, almost 1 millisecond in fluxonium. Flash qubit is a bit worse, a bit from the point of view of the game, but it is still large. And what I want to say is that now there is no point to keeping, well, there is no point. At the level of 1 qubit, these times are large enough because the typical energy is gigahertz, so you could, in principle, do operation at nanoscale time scale if you have enough interaction. So probably the bottlenecks are in somewhere else. And my point is that the bottleneck now are when you couple many qubits. Now, when you couple many qubits, you may have one qubit that is perfect, fine. Now you couple many of them, and then you have to do something for the 1 qubit to be sensible to another qubit. But to be sensible to this other qubit, you have to open the way to this qubit to get some susceptibility to the external fields that the other qubit creates. But if you have sensibility to the external field of the other qubit, you also have sensibility to the noise. And then there comes the problem, I guess. A solution for this is topological protection. But you don't only need protection, you need protection and manipulation. Okay? A partial solution could be also to have a qubit that is protected and you can turn on, turn off the protection very fast. Okay. And this is one of the problems that come when you are coupling many qubits, but there is another problem. There is the problem that even if you don't care about the noise, or the noise is settled, you may have a family of Hamiltonians that you can implement for 1 qubit or 2 qubits that are too poor to do any quantum computing stuff, okay? And this is what I'm going to talk. Well, how do we implement universal quantum computing? Let's say that we want to do an algorithm, and with our algorithm, at the end, what we do is a unitary transformation to the qubits, right? Then we need someone to tell us that we have in the hardware, we have available the tools that we need to implement this unitary transformation. Well, this theorem, they say that you can approximate this unitary with a set of 1 qubit, 2 qubit rotations, one qubit rotation or 2 qubit gates. This is nice. Even more, there has been papers saying that you only need a universal set of gates. For instance, 1 qubit plus a C0 gate, okay? But you have the same for the adiabatic quantum computing. Well, okay. The analogy, I think, to these theorems is that the Hamiltonian for adiabatic quantum computing needs only to have two-body interactions. And furthermore, there has been other references that have said what is the minimal form of this two qubit coupling Hamiltonian. And this minimal form has this shape with coupling in two directions. There are other Hamiltonian that can lead also to universal quantum computing. But for my talk, this is the relevant one. So our goal is to do flash qubit with complex coupling. What do we mean with complex coupling? First, to reach a strong couplings between qubits. This would allow to perform fast qubit gates and also to achieve a wide spectrum of Hamiltonians for quantum simulation and for adiabatic quantum computing. But also, we would like to have a form that is complex enough, at least, that it cannot be simulated with quantum Monte Carlo. Even if we don't reach the general Hamiltonian that I said before with two directions, but at least we should be able to get something that quantum Monte Carlo cannot work with. Because if quantum Monte Carlo works, then it is very difficult to beat quantum Monte Carlo. Okay? Now that we are doing with 2 qubits, we also use the work that we did for this to develop also couplings of this form with a resonator, with a LC resonator and a qubit. And the nice thing is that we have achieved to get a qubit, well, we studied and did theory to understand how to couple in two directions with a resonator. So these A are the bosonic creation and annihilation of the LC resonator. This is a qubit operator, so on and so forth. So let me say that if you want to get a Hamiltonian or a coupling with only this term, this is already made. The D-Wave are very good doing this. D-Wave, what they are doing is to get 1 qubit. They made it to interact with a coupler that can be understood as an LC resonator. So you have this type of coupling, and they interact via magnetic interactions. So when you write in the qubit base the magnetic interaction, you get a sigma x, and you get this guy from the resonator. And then, using this guy from here, you can induce this type of interaction with that can be tuned with the magnetic field. Yes.
Yeah. So what's the range of the couplings in the annealer? What's the dependence of J on I and J?
The range of the
dependence of the couplings JXX and JYY on the distance between qubits in the annealer?
Well, this depends on the architecture that you are using. I'm going to talk about this. Okay. Because one way of inducing complexity is to get only this in this direction, but with very long range. But long range is difficult to do, at least the magnetic one. No? Magnetic interaction, you put one, you put another one. So
yeah, no, I was interested in superconducting qubits.
Yes. But yes, this is an important point. After.
Okay.
Thank you. Okay, so to get this term, what you can try is to do like this paper of D-Wave and put a capacitor here, okay? And then you will, in principle, you think that you will induce a coupling in the other direction. Or also, there are some papers that have worked with a 3 Josephson-Janssen qubit and a resonator. So let's focus. How much time do I have?
No, I don't know.
I see you.
Just been coupling 10 more
10 more
minutes.
minutes? Okay, so we are going to focus now on the chart. This is going to be a bit technical, so I may be a bit fast. But the matter is that we want to induce coupling using a capacitor. So a capacitor is going to give you a capacitance and an interaction between the charge of one qubit and the charge of the other qubit. Okay. Then what we do is we say we have of qubit-qubit or qubit resonator coupling via the capacitor. We know the Hamiltonian for each of the pieces of our system, and then what we want to do is to write this guy in the base of the qubits. Okay, and we do so first by projecting on the qubit base. On the qubit base is very easy. Well, very easy is not very difficult. You can get that here this Q goes to sigma I, and there is an important point that there is a gap here. This is the gap of the qubit. Then getting this projection, these are the charge operators projected onto the qubit base. Okay? And then you can work now the guy, the interacting guy, and it gives you, for the qubit-qubit coupling, it gives you a coupling in the y-y direction, that is this one, divided by the gap. This itself is very bad news for a quantum annealer, because in a quantum annealer, in a adiabatic quantum computer, you want to start with something that is dominated by the gap, and then you run the algorithm, and you end up with something that the gap should go to 0 and the interaction should be very large. You cannot do this with this, because there is a G over delta is proportional to delta, to the gap of the qubit. But also you can do the qubit resonator with these formulas, and you get this formula, which doesn't have this problem. Well, it's a formula that depends. This is the minimum of the potential of the inductive potential. Okay. Now, does this work? Well, for a small coupling should work, but for large coupling doesn't work. Why it doesn't work? Well, it doesn't work. It depends on the system. That if you want to write things correctly, you need to use the Riefer-Wald transformation, but you need to get the full series of the Riefer-Wald transformation. So the thing that I did before, it was the projection to the qubit subspace, but then you have many more terms. And those many more terms, you can think like in perturbation theory, that in perturbation theory you have in the numerator, you have the coupling of states via the perturbation, and the perturbation now is going to be the operator that brings the system from the qubit subspace to the sighted one, and in the denominator you have the energy of the difference between the state that you are linked with the perturbation. Okay, if you do this and you try to apply to the system that we were talking before, it is a flash qubit and a resonator of two flash qubits. What happens is that for the qubit resonator, you have the coupling at first order that works well, because here this guy goes as with this formula, where this is the qubit gap and this is the resonator frequency, and this is when you divide it by h bar the qubit frequency, which is supposed to be well, qubit frequency, no, this one, the difference between the qubit and the sighted state. Then this goes to 0 if you put a high m. So you can forget about all the other terms beside the first one. But for the qubit coupling, this doesn't work. So the qubit coupling, you have to study the full series, which makes things much harder. Well, now the summary of what we did is that we were able to design a flash qubit with high harmonicity coupled to a resonator with a capacitor and get these terms. Also, we explained it that this coupling strength follows the first order approximation that I was showing in the previous slides. But with the qubit coupling, we had to perform the full Riefer-Wald transformation, study the full series, and we obtained also this type of coupling with two directions, but not which are not arbitrary. You cannot choose the strength of this direction and this direction independently, at least for a strong coupling. We are thinking to apply similar techniques to other type of qubits. But before doing so, let me say a couple of things is that we have not gotten the full tunable Hamiltonian that I put at the beginning that allow universal quantum computer. Still, they are non-stochastic. However, there are a couple of papers that have said that even if they are not stochastic in the qubit base, you can simulate it with Monte Carlo in the full circuit because they are stochastic in the full circuit system. I think that this, strictly speaking, doesn't apply to our system of 3 Josephson junction arrays qubit, and it is still non-stochastic in the full circuit base. Anyway, if I have more 5 minutes, do I?
Yeah, around that.
Okay. I'm going to talk about another way of inducing complexity. So up to now, what I'm focusing is inducing complexity in the form of the interaction. Okay? Complexity means to produce models that classical methods cannot work with. But there is another way that is related with your question. The other way to induce complexity is to forget about this universal quantum computer as D-Wave is doing, because it is too complicated to have these 2-direction couplings, and then do something, do whatever you can do, I guess. And then what is this whatever you can do? I said that it is easy to induce magnetic interactions in with the flash qubit, and this is something that D-Wave has already done, and is very good doing that. So we will have a general Hamiltonian for doing annealing. This is the annealing scheme. You start from H node that has a simple form, and we end up in this H, which is the problem, that has coupling all in one direction. Now, we can say, okay, quantum Monte Carlo can do that. Or even, if you want to solve this problem, we can use Monte Carlo to solve this, no? But it depends on the range of the coupling that you set. So, if we put this matrix that is one nearest neighbor, then everything is going to be more than trivial. There is no quantum computer need to solve a model like this. This is a classical model with nearest neighbor coupling in one dimension, not difficult. But if you get something that is fully connected, you are going to have something very difficult. Monte Carlo can be used, but Monte Carlo is not going to work well because there is a spin glass phase transition. And the nice thing of the spin glass state is that you cannot even approximate with classical methods for a system large enough. You cannot even approximate the low energy states because spin glass is an NP-hard problem. But there is many details in this NP-hard problem stuff because you may have an NP-hard problem that the ground state is very difficult to get, but it is very easy to approximate. Well, easy, or it is the low energy states are easy to approximate. If you have something like this, there is, again, no need to do a quantum computer because Monte Carlo is going to give you the solution. But the spin glass phase, it is very hard for any classical method to get inside the spin glass phase. So let's see if a quantum computer or quantum annealing using quantum fluctuation can get there. And this is the direction that it seems that D-Wave is doing. This is the paper. I think that this is 2024. I made a mistake. No. This is 2024. They claim, again, that they have achieved quantum supremacy with a quantum simulator using a system that simulates a spin glass. In here, they also said that they are also dealing with spin glasses, and they said that they can do something that Monte Carlo had many difficulties to perform. The way that they induce the spin glass is to allowing long-range connection, everyone with everyone, but this is not made at the hardware level. They set a bunch of spins of qubits that link this qubit with this other qubit, and then they made an effective connection between qubits, far away qubit in the chip. Okay, so they use embedding. This is embedding. You embed a hard problem that is highly connected to another problem that has many more qubits, and the connection, the embedded connection, are made by a ferromagnetic interaction between a string of qubits. Okay, so our approach here was to try to see if you can induce a spin glass phase with something simpler at the hardware level. We forget about embeddings, and we see if we go deeper in the hardware level, if we can get a spin glass phase. Well, the bad thing of the, or relatively bad thing of the spin glass phase is that in quasi 2D graphs, there is not really a spin glass phase at low temperature. There could be a spin glass state at 0 temperature, but not the phase. Then again, it may be easy for Monte Carlo to approximate the low energy eigenstates of the spin glass. So, because of this reason, people started to say that it is maybe better to do something that has not so many connections, but still has some sort of non-locality. And this is a random regular graph. With a random regular graph, you have a finite amount of connection, but connection can be non-local. Each qubit is connected to another 3 qubits, but in a non-local way. In this model, you have a spin glass phase. So, well, we were examining these two problems, and what we found is that still, even if 2D spin glasses may seem that are not so good for a quantum annealing, we get to the conclusion that it may work. How it may work? We were computing the correlation time in the parallel tempering. We did parallel tempering, and with the parallel tempering, you have to wait time much longer than the correlation time of your sequence. And this is the time that you have to wait typically for the system to be thermalized. And then this time, the matter is that when you grow the system, it exploits if you are in a spin glass phase. So this is a proof, let's say, of the complexity of doing Monte Carlo in this type of systems. So if we have the random regular graph, and I said that there is a spin glass phase here, we got a signature of the spin glass phase in this time, in the log of the time, typical time that takes Monte Carlo to be run, okay? And we have a crossing point for different sizes, so usually this signal a phase transition, and indeed, the time after this crossing point, it sharply goes to be much larger. Okay, when we did the same for the chimera, which are the D-wave lattices, Zephyr, and so on, we also get a crossing point, but this crossing point doesn't mean that there is a phase transition because it swifts slowly to the left. So the phase transition is starting to move to the left when you increase its size. This means, or at least is consistent with the fact that there is no spin glass phase in 2 dimensions. But the matter is that if this pseudo-critical point is with a temperature high enough, occurs for values high enough with temperature, which is here, it may work. Monte Carlo may have a lot of difficulties to solve these problems also, okay? So we thought that maybe one way to produce simpler hardware connections and still get difficult models was to find the system that has the pseudo-critical temperature, this crossing point, the higher in energy that you can, and then to have the sharper increase in the time that takes Monte Carlo to run as a function of n, of the system size. And with this I'm finished, so let me say the summary. First thing is that I always find that the people focus too much in noise. I don't know if this is the correct, at some point I started to think that maybe people should move from noise to study the connections and see what happened with the connections. And I think that an important restriction in the hardware of superconducting circuit at least is the type of connection that you can get and the strength of the connection, so that you don't have to spend your whole life doing a gate. And taking into account this, there are 2 paths to see quantum advantage in adiabatic quantum computing with superconducting circuit. I think that one of the paths is to obtain general form of coupling that makes impossible for Monte Carlo, quantum Monte Carlo, to simulate the system. And the other part is to forget about this non-stochasticity and then try to get long-range models in 2D also that produce the higher pseudo-critical temperature for the spin glass, low temperature spin glass phase. And with this, I would like to thank you, and I am open to questions.